Okay, I'm gonna just go ahead and go here. All right. There's our video. All right. Okay, so what I'm gonna do today is kind of extend upon what I did last week or last time I saw you guys. So the last lesson we did, I think I extended upon the bases and using KBs, finding those things from KAs. Today's lesson kind of extends upon that in that it looks at things that mess with pH that don't look like they should mess with pH, where it's not so obvious. Now, if you look on Appendix D, there's like a zillion different acids there that influence the pH of something, and there's some bases on the next page that influence the pH by messing with the pOH. We're going to look at today is we're going to look at salts, what a salt is, and salts that can mess with pH. We're going to look at things that do mess with pH and things that don't mess with pH. Okay. So the thing about, and I'll share, I can put these slides online if you want them online or whatever as well with the video, just if I go too fast or whatever. Salts are ionic compounds that are made from acid-base reactions. One of the definitions that we use for that is in that an ionic compound is usually a metal and a non-metal. It doesn't always have to be. You'll see some examples in a second that are not metals and non-metals, but they have positive ions and negative ions that come together. And a lot of times when you have a traditional like kind of titration reaction, it makes salts. So like, for example, last year we needed titration, we had HCl, we reacted with NaOH, we made NaCl, we made traditional table salt. Here's an example of something that we're going to eventually figure out. This is a salt that involves two parts. It has the ammonium ion, NH4, and it has the fluoride ion, F. And going back into like what we did last week, maybe you'll remember this is something that has a positive ion that can mess with the pH because it's a conjugate of a weak base, and it has a negative ion that can mess with the pH because it's a conjugate of a weak acid. So I'm going to show you guys eventually how to deal with that and how to figure out, okay, great, is that an acid or a base? Okay. So NH4 plus and F minus would be the ions that make up this salt. A lot of the salts that we're going to look at, though, are going to be much easier than this. They're going to only have one part that messes with the pH. So they won't have two parts. And like I said, that's going to be the last thing that we deal with is trying to figure out, okay, if you have a salt like this, is this or does this salt make something acidic or does it make it alkaline? Okay. So this means that salt solutions can be both acidic and basic. Now, salt solutions can also be neutral because it's possible to have both parts not do anything to the pH. So we'll look at why NaCl does not change the pH of a solution. You can dump as much NaCl in a solution and it's not going to mess with it. But if you dumped NaF into a solution, it would mess with it. So we're going to look at the reasons why today. And I think this lesson today, like I said, I hope it's not going to go that long. It's going to solidify the whole what to look for when you're trying to figure out things that mess with pH that are not obvious. That's my goal. Okay. So salts and dissociation. Most salts will dissociate 100%. The things that don't dissociate 100% are precipitates, which I don't know. According to our timeline in the next few weeks, maybe we'll get to it. I have no idea. Okay. But water will cause salts to dissociate and break up. And what happens is that the different parts can both react with water. The ones that truly react are the things that influence the pH. So when you look at NH4F, it has two things that can react with water. Okay. And the pH of solution is going to be predicted by looking at the ions of these salts. So once again, we won't get to this yet, but I'll just go ahead and write it out right now. So let me make this a little bit bigger so you guys can see it. Okay, so NH4 plus can react with water in that this is an acid because it's the conjugate of NH3, which is a weak base. So it gives its H here, and we get H3O plus, which is the same as H plus for us, and we get NH3. Okay, so that is one part of the salt acting as an acid. Okay, the other part of the salt, and we'll break this up into positive things and negative things that can influence pH. The other part of this would be F minus reacting with the water that it's swimming around in, acting as a base because F minus is the conjugate of a weak acid, making HF and making OH minus. Now here's the whole thing. With NH4F, we're going to look at, okay, if both of these things happen, the thing that is making more of either this or this is going to determine if it's an acidic solution or a basic solution, okay? So this is what happens when both things can do that. And I'll show you a very easy way to tell if something's an acid or a base by the end of this lesson, all right? So what we're going to do is we're just going to look at one part at a time, okay? We'll start with the anions. Those are the negative charged things in water. And the general reaction of an anion, I just use the value, or used X. X minus reacts with water. Water acts as the acid. Anions for us, most of the time, not always, and you'll see why in a second, most of the time will act as a base. So it'll act as a base. Come on in.
I didn't check in.
Oh, I don't have much in there. Sorry. Just
Okay.
doing the trash. Okay. So this is what we're trying to make here, is make this OH minus. All right. So here is the whole key, and this is the clue. If it will mess with the pH. If X minus is a conjugate of a weak acid, so basically, if X minus is something on the weak acid chart there, it's probably going to be a weak base. Examples. F minus. Okay. HF is a weak acid. That's a weak base. It's going to affect the pH. Okay. Other examples. Maybe something like CO3 2 minus. CO3 is the conjugate of HCO3 minus, or what you'd find on that chart, H2CO3. So if this is a weak acid, that's probably a weak base. It's going to mess with the pH. That's what you're kind of looking for, is looking for a piece, just like we did last week or whatever the last time I saw you guys. Okay? Here's another key rule. If it is the conjugate of a strong, it does nothing to the pH. So if it's not on that chart, it's not going to influence the pH. I'm not going to go into too much detail on why this doesn't happen, but basically, let's say we had Cl minus, okay? Now, you might think, all right, that's going to be a base. But if you look, you would not find HCl anywhere. And the reason you wouldn't find HCl is because it's not a weak acid. It's not on that chart. So Cl minus, when it tries to react with water and make HCl, okay, by the way, you don't have to write this down because this reaction is bullcrap. It doesn't happen. Here's what happens. The Cl minus is such a weak base that it cannot even pull that H off of there. Plus, what we know about HCl is that it is a strong acid, so any reaction it's going to have is going to go back the other way. So it just doesn't happen. So key for you guys, if it's a conjugate of a strong acid, it's not going to do anything to pH. So here's some examples of things that would not do anything to the pH. Cl minus wouldn't, Br minus wouldn't, I minus won't. NO3, which is nitric acid's conjugate, it won't do anything. Okay. H2SO4, we can't mess with that because that's got a little exception there. Okay, so those are kind of the main ones. If you see those ions, they don't do anything to the pH. Okay? Any questions about what just happened there? Do you understand where I'm getting these things? I'm basically just using Appendix D. So Appendix D is the easiest way to figure out if something's going to make a solution basic or not. Okay? That's if that anion. So a couple of examples here. Cl minus from NaCl. So we know Cl minus is the conjugate of HCl. That doesn't do anything. This one in your book is written like this. That's the acetate ion. I think it's it's like towards the top, might be the top one. So when you see the acetate ion, you got to think, all right, we won't even worry about the beginning here for right now because I'll show you that in a second. But you got to think, all right, if I see that, then it's a weak acid, so that's probably a weak base. That's going to make the pH go up. Does that make sense, guys? I don't know. It's convoluted and tough to probably learn online. Okay, let me talk about the cations in water real quick. The cations in water would be the positive charged things. Cations in water can you have some metals that can change the pH and some do not. I'm not going to go into too much detail. I'm going to give you a couple of metals that can make the pH more acidic. Here's the ones that don't change the pH. So basically, anything that's group 1, okay, and then Ca, Sr, Ba, very heavy metals. That's hard to what the heck is a very heavy metal? A very heavy metal would be something like gold, something like platinum, something like lead. Typically, we don't have any kind of change to pH, okay? So what's the easiest way to remember this? Well, here's the deal. Group 1 metals, Li with OH is like a strong base. So this is kind of the whole idea. If you are the conjugate of strong, you don't do anything to pH. So Li and Na and what else? K and all those guys, they don't do anything to the pH, okay? The easiest thing to figure out that these things that do influence the pH, okay, I'm going to tell you iron 3+, okay? That's going to be the one. This is a type of acid that we don't spend too much time on until you get into a lot of college chemistry. And even then, I bet you don't spend too much time on it. But if you see Fe3+, it's acidic, okay? Just log that. Put that in your brain. Fe3+ is acidic. It is a Lewis acid. So what Fe3+ does essentially is it reacts with this, and it wants to join with the OH and leave those guys like that. That's why it's acidic, okay? But don't worry about that. Just know that Fe3+ is an acidic metal. The other cations that are going to be acidic would be things that, and I just grabbed a couple of them, things that are from your weak base chart but are conjugates. So NH3 is a weak base, NH4+ is a weak acid. Methylamine is on that chart. It is a weak base, C3N3H+, that's its conjugate, that's a weak acid. Those things will decrease pH. So be on the lookout. What kind of cations mess with pH? Here's the deal. A lot of problems that you guys are going to see, the cations you can just kind of cross out. Because unless it's iron 3+ or one of these derivatives, then you don't have to mess with it. Okay? What questions do you have? Any? So, kind of our little flow chart and kind of combined effects of these things in solutions. Okay? So this is kind of a summary of what we just talked about. And then we'll do one example and then we'll be done. If the cation and anion do not react with water, there's no pH change. If you want an example of that, we would say NaCl. Very easy. Group 1 metal doesn't do anything. Conjugate of a weak acid or strong acid doesn't do anything. Okay? If just the cation reacts, it's going to decrease the pH and it's going to make it acidic. Okay? So just the cation. What would be an example of just the cation? I'll give you two. Let's say we had FeCl3. Okay? FeCl3. Fe is at iron 3+. Cl doesn't do anything. So if you see that, oh, that's an acid. Okay? Just one of those things to log. Here's another one where just the cation would react. NH4Cl. NH4Cl. So we know that Cl doesn't do anything since it's the conjugate of strong. NH4 is the conjugate of a weak base, so it must be a weak acid, so it's going to decrease the pH. Those are some examples of things that would decrease the pH. And by the way, you don't have to calculate anything. You can just look at it and just tell. Okay? I'll show you where we have to do a calculation. Just the anion reacts. That's going to increase the pH, or it's going to make it more alkaline or base-like. Okay? So what does that mean? Just the anion would react. So here's an example of just the anion reacting. We have LiF. Li is a group 1 metal. We just learned that group 1 metals we can just cross off. F is the conjugate of a weak acid, which is HF. So that means that F minus is going to be a base. Here's another example, just the anion reacting. Oh, geez, let me think here. Just the anion. So we have KClO2. Okay, this one you'd have to probably look a little bit more. But K is a group 1 metal. We get rid of that. ClO2 is on your weak acid chart because it is the conjugate of that acid right there. That would be like a base. Okay? And the last one, and by the way, you don't have to even do any calculations for that. That's why this assignment's going to be pretty nice. I think you'd be able to look at stuff and go, oh, that's an acid, that's a base. No actual calculations. The only time we have to calculate something, I'm going to show you how to do that, and then we'll be done, is when both things react. Okay? When both things react, this is the hard one. You've got to look at their Ka or Kb values. The larger K will tell you which one influences pH more. So if I had something, right, and it looked like, oh, that can be an acid or a base. We call those things amphoteric. It's like sometimes it's an acid, sometimes a base. It depends on what it reacts with. Usually those things will have two things. So you need to watch out for these. Okay, they'll have two things. The first thing it'll have is an H written at the beginning. Okay, it'll be H something and then some kind of negative charge. Maybe -1, -2, -3 would be too much. It's either going to be a -1 or -2. Those are going to be the ones you actually have to calculate. I'm going to show you guys how to calculate that on the next slide. Okay? So literally, if you can remember some basic rules about this stuff, knowing the strong acids, knowing the strong bases, you can eliminate those guys, those conjugates, because they don't influence the pH. All right? So, our question, will the salt Na2HPO4 form an acidic or basic solution? So this is the one that's going to probably be, these will be the toughest ones. Will the salt Na2HPO4 form an acidic or basic solution? Okay? So what you have to do is I think the easiest thing is just identify what does nothing. Okay? I see something that would not influence the pH that I can just go ahead and just shank. Right? The thing that I see is the Na. It's a group 1 metal. Group 1 metals don't influence pH. So here we run into a bit of a problem. What we're looking at is this chemical right here, HPO4, and it is a 2 minus. If you're wondering how I know it's a 2 minus, well, Na is a +1. There's 2 of them, so that would have to be a 2 minus to cancel that out. So this falls into that amphoteric. Is it an acid? Is it a base? What we have to do is we have to find the Ks. So what we're going to do is a couple of steps. The first step is we're going to write and pretend that that thing is an acid. And we're going to figure out what its K is. And I will just tell you, that's going to be the easier of the two here. So if this was an acid, okay, if that was an acid, that means that this H, and you could write this with water or without water. You can make H3O plus or just make H plus. We're going to go the easier route here. This would make H plus, and it would make PO4 3 minus. Okay. Now, what we have to do, because this is an acid, is we have to figure out what the Ka of this one is. So I'm going to give you guys a minute to look at the chart. And here's the problem. This is what's tough about this, is that you have to find and pick the correct Ka. H3PO4 has 3 Kas. You got to pick the correct one. So I'm going to give you guys 30 seconds to figure out which one is the correct Ka, and we're going to write that value down. Is it Ka1? Is it Ka2? Or is it Ka3? Right? So now you have 20 seconds. Somebody unmute and tell me your thoughts on which one you picked. Or if you don't know. What'd you pick, Jay?
Would it be the third?
I think it's the third one. Yep. I think it's the third one. The reason it's the third one is because the first one would be for the first H, that'd be H3. The second one would be for the second H, that'd be H2. And the third one would be for that one. So we're looking at 4.2 times 10 to the negative 13. Okay. There you go. We have any questions about that? Yes, no? Okay. So we're going to have to figure out what the KB is, and this is going to be the thing that's a little bit tougher. So let me show you how to deal with this. If this thing were a base, we're going to take the exact same chemical. We're going to react it with water because we want it to act like a base. So instead of giving the H, it's going to take the H. So this H is going to go here. It's going to make H2PO4 minus plus OH minus, right? This is not going to be a Ka because this is a base. We need a Kb for this value here, okay? So the question is, like, how do we even find Kb? Like, where's the Kb going to come from? I will give you a hint. I need to use my calculator because I can't do this one in my head. All right. So the Kb comes from a conjugate of a weak acid. Let me show you the trick on picking the correct K. Because obviously you guys see there's 3 Ks that we can divide Kw. You guys understand we have to divide Kw from one of the Kas? Do you guys get that? Okay. So we have to pick the correct one. The question is, do we divide Kw by K1, K2, or Ka3? Right? So here's the easiest way to do that. Right? A lot of people pick the wrong Ka. They pick Ka3. They want to divide by Ka3, but that's not the K you divide by, because that would be if it was PO43 minus. Easiest way to do this is to look at your products and look at that reverse reaction right there. That's going to be the Ka that we want to pick. So what you have to do is you have to figure out which Ka describes H2PO4 minus. 1, 2, or 3? I'll let you guys unmute and tell me.
1.
Close. I'll give you a hint. It's between 1 and 3.
2.
There you go. Okay, now here's why. Here's why it's not 1. If it was 1, that would be fully loaded. It'd be H3PO4. That's for Ka1, right? This one is kind of in that middle ground. And because of that, it's Ka2. So what we do is we take Kw divided by whatever Ka2 is. So 6.2 times 10 to the negative 8. So Kw is 1 e negative 14 divided by 6.2 e negative 8. All right, so we get 1.6 times 10 to the negative 7. Okay. Here's the rule. Bigger number wins. All right, so we're looking at the exponents to figure out the bigger number. If it's an acid, that's its K. If it's a base, that's its K. Does everybody see here that the base number is quite a bit bigger than the acid number? So this salt is most likely going to be slightly alkaline. It's going to be basic because Kb is bigger. All right? It's a lot of stuff on online teaching. Sorry about that. That's it. So, summary. Will a salt make something an acid or a base? Depends on what's in the salt. Okay? You can look at the cations and the anions and eliminate the easy things. If both things are conjugates of weaks, then you have to do this process. This is the only time you have to calculate anything. For us, for me. Okay? Okay. I'm going to just stop there and take your questions if you have any. Like, for example, where did you get blank? Where did you get this? Where did you get that? You know, where did you pull this number out of? Why did you pick Ka2 and not Ka1? Why did you use Ka3 up here? I don't know. Okay. I'm going to stop recording and you guys can